Okay, so when you hear the name Gauss's law, I bet your mind probably jumps to some scary, complicated equation, right? But what if I told you it's actually one of the most elegant and powerful shortcuts in all of physics? It's a tool that lets us solve problems about electric fields that seem totally impossible, but with, a surprising amount of ease. So here's our game plan for today. We're going to start with this core idea of electric flux, then see how that leads us straight to Gauss's amazing law. After that, we'll put it into practice with a real calculation and then wrap it all up with the key rules you've got to know.
First things first, we absolutely have to get our heads around a concept called electric flux. Trust me, it's the key that unlocks everything else, and it all starts with trying to measure something we can't even see.
I want you to imagine an invisible electric field is kind of like the wind. How would you measure how much wind is blowing through an open window? See, it's not just about how fast the wind is blowing. You also have to think about how big the window is and what angle it's at, right? Well, we have the exact same challenge with electric fields.
So to solve this, we do what physicists do best. We break the problem down into tiny, manageable pieces. We've got a charge Q sitting in the middle creating an electric field, E, that just radiates outward. Now, instead of trying to figure out the whole sphere at once, we're just going to zoom in and focus on how much of that field pokes through one tiny little patch of the surface, an area we'll call delta S.
And this measurement, this flow, it has a name. We call it electric flux. For that one tiny little patch, we calculate the flux using something called a dot product. Now, don't let the name scare you. All it really means is we're multiplying the area of the patch by the part of the electric field that's poking straight through it, perpendicular to the surface. It's how we account for both the field's strength and the angle, just like our tilted window in the wind.
But here's the problem. To get the total flux for the whole shebang, you'd have to do that calculation for every single little patch and then add them all together. For any shape that isn't ridiculously simple, this becomes a total nightmare. It's an incredibly tedious, if not impossible job.
And this is where the story gets really, really good. A genius named Carl Friedrich Gauss came along and found an incredible shortcut, a way to bypass all of that painful math. And honestly, it's one of the most beautiful ideas in all of physics.
And boom, here it is. This simple-looking equation is Gauss's law. It tells us that the total flux, that's capital Phi, through any closed surface is just the total charge you've trapped inside divided by a constant. That constant, epsilon naught, is called the permittivity of free space. You can just think of it as a fundamental number of the universe that tells us how easily electric fields can set up in a vacuum.
So what's the big takeaway here? It's this. You can forget about all those millions of tiny patches on the surface. The shape of the surface, its size, whether it's got bumps or dents, none of that matters. All you need to know is the total charge living inside that surface. It's this incredible direct link between what's on the inside and the field on the outside.
All right, so the theory is elegant for sure, but where does the real power come from? Let's put this thing to work and see it in action.
Now, the law works for any surface, but it basically becomes a superpower when we use it on things with a lot of symmetry. Take a look at these examples from the text, a sphere and a cylinder. Because their shapes are so uniform, the math becomes incredibly simple. And that's the secret sauce. We get to choose an imaginary surface, a Gaussian surface, that perfectly matches the symmetry of the problem we're trying to solve.
This slide really just lays it all out. On the left, you've got the brute force method, summing up countless little pieces. It's like trying to count every single grain of sand on a beach. And on the right, you've got Gauss's beautiful solution. Just find the charge inside. It's like skipping the counting and just weighing the whole bucket of sand instead. Way easier.
Okay, to really see this thing flex its muscles, let's get our hands dirty and walk through a full numerical example, pulled straight from the source material. Okay, here's our setup. We have a cube sitting in an electric field. Now, the important thing to notice here is that the field isn't constant. It actually gets stronger as we move along the x-axis, from left to right. Our mission, should we choose to accept it, is to use Gauss's law to figure out the total charge, Q, that's hiding somewhere inside this cube.
So here's our plan of attack. The electric field is only pointing in the x direction, so we really only have to worry about the flux going through the left and right faces. Now, for the left face, the field is going in, so the flux is negative. For the right face, the field is going out, so the flux is positive. We just calculate those two values, add them together to get the total net flux, and then we use Gauss's law to solve for the charge. Easy enough, right?
So, after we run through the math, what do we find? Well, the flux coming out of the right side is stronger than the flux going into the left. That means our net flux is positive, which tells us there has to be some positive charge inside. We plug that net flux into Gauss's law, and we get our final answer, 9.27 picocoulombs. And here's the magic part. We found the exact amount of charge without ever knowing where it was inside the cube. It could be one little point. It could be smeared all over. Gauss's law just doesn't care. How cool is that?
So this law is obviously super useful, but like any powerful tool, there are a few important rules of the road that we need to follow to make sure we're using it correctly.
Let's run through these real quick. First, remember, this law works for any closed surface you can dream up. Second, Q is the net charge. That means you add up all the positives and subtract all the negatives inside. Third, any charges outside the surface, they definitely affect the E field, but they don't change the total net flux. Why? Because any field line from an outside charge that goes in must also come out, so it cancels itself out. And finally, the whole secret to making this law easy to use is picking a clever Gaussian surface that matches the symmetry of your problem. That's the real pro move.
All right, let's pull all this together. We'll summarize the essential ideas and formulas into one neat and tidy toolkit for you.
So this slide is basically your cheat sheet. We started with the definition of flux for a tiny little area. Then, we unveiled the absolute star of the show, Gauss's law, which brilliantly connects that total flux to the charge trapped inside. And it's all built on the bedrock of physics, the fundamental description of the electric field from a point charge, which comes from Coulomb's law.
So I want to leave you with this final thought. Gauss's law is a truly beautiful statement about how electric fields work, but the principle behind it applies anytime you have a force that follows an inverse square law. And you know what other fundamental force does that? Gravity. This powerful way of thinking isn't just a neat trick for your electricity homework. It's a deep concept that pops up all over physics. So what else could you apply it to?